Bismillah Rahim. My name is Dr. Muhammad Iqbal, and today the topic of my presentation is efficacy of alkaline bending material for immobilizing lead in soil polluted with industrial effluents. My department is Department of Environmental Sciences and Engineering, Government College University, Faisalabad, Pakistan. Introduction. Lead polluted soils are malefic for the environment. Lead polluted soils deteriorate crop quality. Lead polluted soils have negative impacts on human health. First of all, lead polluted soils are malefic for the environment because lead leads to groundwater, reduce soil productivity, and depreciate land price. Lead reduces crop quality by reducing crop yield, crop quality, poor nutrition, not fit for human consumption, and negative impact on human health by producing several diseases such as cancer, nervous system disease, renal failure, immune system, reproductive and development systems. Hypothesis of this study was amendment of magnesium potassium phosphate cement, which is an alkaline material, can reduce lead phytoavailability in lead polluted sediments. Here we come to in situ immobilization idea. In situ immobilization of lead in polluted soils. The term immobilization is the process of fixing heavy metals such as lead, nickel, cadmium, copper in the soil by using soil amendments to reduce mobility of metals in the soil and reduce lead uptake by the plants. There are several amendments that can be used in soil, such as organic and microbes. In organic, biochar, compost, and cartosines are the most common one, while in microbes, bacteria, avascular mycorrhiza, fungi, and alga, they can also serve the purpose of metal immobilization in the soil. So the objective of this study were roles of magnesium potassium cement for immobilization of lead in lead polluted sediments, lead concentration in biological indicators like Tussa sativa and Acinia fetida. To estimate lead concentration in different chemical indicators, ammonium nitrate, calcium nitrate, DGT, and soil water extract. Correlation between lead concentration in biological indicators and cost-effective dose of MKC for remediation of lead-polluted sediments. Materials and methods. Soil. We gather lead-polluted soil sediments having 711 milligram per kg lead in soil due to lead battery effluents. The treatments that we used in our experiment were MKC 0% that we set control, MKC 0.5%, MKC 1%, MKC 1.5, MKC 2, and MKC 2.5%. These are the sediment properties having pH 6.60, EC 1.99, CEC 12.9, organic matter 6.8, calcium carbonate 37%, TTP extractable lead 2.90 milligram per kg, total lead 711 milligram per kg, exchangeable potassium 103 milligram per kg soil, and available phosphorus 8.50 milligram per kg soil. MKC properties. The pH of MKC was 9.2, electrical conductivity 9.3, magnesium 159.6 gram per kg, phosphorus 119.7 gram per kg, potash 152.3 gram per kg, oxygen 534.8 gram per kg, boron 3.4 gram per kg, and hydrogen 30.2 gram per kg. Studied parameters. Here we used biological indicators like Tussa sativa that were grown for 50 days in amended soil, and Acinia fetida, which is called earthworm, that were kept for 50 days in amended soil. Chemical indicators were different type of extracts like ammonium nitrate, calcium nitrate, DGT, and soil water extract. Note, all these biological and chemical indicators were performed according to the treatment plan. So the studied parameters Of biological indicators were lead concentration in shoots and roots of Lactusa sativa, biomass of shoot, antioxidants. Similarly, for earthworms, lead concentration in worms, biomass of worms, and antioxidants of worm. Similarly, in extracts, we measured lead concentration. All these analyses were done with ICP-MS, inductively coupled plasma mass spectrometer. Antioxidants were done by standard protocols. So it is the flow chart of the experiment. We got sediments and we mixed MKC in it. Then the amended sediments were subjected for 50 days incubation with earthworms, 50 days growth of Tussa sativa, and extracts obtained after 60 days and DGT deployed after 50 days. So after that, all these parameters from these four subsections of experiments were measured. Results. Here in figure 1, we can see that biomasses of biological indicators. This is shoot biomass A of Lactusa sativa, and here it is the worm biomass. Here we can see that MKC 2%, 2.5% were significantly at par for shoot biomass and significantly par for worm biomass. Antioxidants of plant and worm. We measured EPX in plant, SOD in plant, whereas catalase in worm, SOD in worm. In APX and SOD in plants, MKC 2 and 2.5% were par with each other, whereas in catalase in worm, same results were found. In case of SOD, highest SOD concentrations were found in worm with MKC 2.5%. Lead concentrations in plant and worm. In plant shoot, lead concentration were least with MKC 2.5 and 2%, both in root and shoot. Similarly, in worm, the lowest concentration of lead were found with 2 and 2.5% MKC. DDP extractable lead also followed the same pattern. Soil enzymes. Here we can see soil enzymes, soil catalase, and soil urease. Both were significantly highest in MKC2 and 2.5%. Lead concentration in different extracts, calcium nitrate extract, soil water extract, ammonium nitrate extract, and lead concentration in DGT. Here we can also observe that both 2 and 2.5% doses of MKC were at par with each other and showed the lowest concentrations of lead in soil. Now we can see the correlation of lead concentration in extract and lead concentration in plant, shoots, roots, and worm. We found a very strong correlation between lead concentration in extracts and lead concentrations in plants and worm. In this screen, we can see correlation between lead concentration in soil water extract and lead concentration in plant, shoot, root, and worm. So shoot lead, root lead, and earthworm lead also have shown strong correlation with lead concentration in soil water extract. Similarly, here we can see lead concentration in ammonium nitrate extract and lead concentration in shoot lead, root lead, and earthworm lead. Here, all three correlations are also very strong. In this correlation, we can see that lead concentration in DGT versus lead concentration in plant, shoot, root, and worm. Here, all these correlations are also greater than 0.9%. Conclusions. Biomasses and antioxidants, plant and worm, and soil enzymes were the highest at 2 and 2.5% MKC rate. Lead concentrations in chemical indicators and biological indicators were lowest at 2 and 2.5% MKC rate. correlation between chemical indicators and biological indicators was greater than 0.92. The 2% rate of MKC was most cost effective compared to 2.5% MKC rate. The MKC can convert lead into insoluble compounds such as steroid K encapsulation and pyromorphite, thus can remediate lead-polluted sediments. Thank you very much for your attention and time. These are the references. Thank you very much.